Hey, AP Stat students, Mr. Mitchell here. Hope everybody's doing well. We're going to take a look at sampling distributions today. Hopefully you've already had a chance to look over the notes, but we're going to take a look at a couple things. We're going to take a look at your data. If you recall yesterday, you were supposed to submit some data where you rolled a die 10 times and recorded the number of 4s out of 10. And then you did that 10 times. So you essentially rolled the die 100 times, but we broke it up into 10 individual sections, 10 trials, if you will, of 10 each. So I want to share with you that data. I put it all into a Excel spreadsheet and then made a table out of that. So I do want to share that with you. So you can see here are all the students. 24 of you. And then here's the results of how many zeros you got, ones you got, 2s, 3s, and 4s. There were no 5s or higher. Okay, so looking at this graph, the left side is frequency, how many times it occurred. This is the number of 4s out of 10. And we're rolling dice, or die, I should say, for singular. The one thing I couldn't change on here, it was fighting with me, so I stopped fighting with it. This isn't 1, it's 0. This isn't 2, it's 1. This isn't 3, it's 2. This isn't 4, it's 3. This isn't 5, it's 4. So it wouldn't let me put 0 as the first thing. I don't know why. It was just being goofy. I know there's a way to do that, but for whatever reason, it was fighting with me and not letting me do that. So you could see that all students were in this area, okay, in this range. I was surprised we didn't get a couple 6s, or I'm sorry, a couple 5s, not 6s, a couple 5s. But I'm not surprised that nothing else above that happened. Reason being, it's a 1/6 probability, okay? And just your mean and standard deviation kind of dictate that you should be down here. It should end up being a skewed right distribution, okay? Not really anything happening down this way, but you usually get a couple to kind of make it look skewed. But if you do it enough times, it eventually does approach normal. Okay, so I was thinking it'll be a little bit 100. It starts to approach normal, but I was still thinking we were going to get a 5. If you look at it, just take a look at the first student that I entered the data. You can see they had no zeros, 4 1s, 3 2s, 2 3s, and 1 4. And you could look down through and see that things were vastly different for certain people. And that's typical. That's part of what a sampling distribution will end up giving you. But again, as you do it more and more, it will turn normal or more normal, approximately normal, I should say, never gets to be quite normal. So this is what our data look like. This is what we got. You can see the totals are at the bottom. Okay. So that's kind of what that is. All right, so what's the definition of a sampling distribution? Sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from that same population. Okay, so we need to get a couple words in here that we haven't really talked about. They've been thrown around a little bit, but statistic is anything that comes from sampling. Any numbers that you run, there's a mean that's a statistic, there's a standard deviation that's a statistic. Those are coming from samples that have been taken, and then you calculate that. A parameter is any number that is calculated or taken from a population. So we need to know, we've used the different symbols before, and I think we kind of define them a little bit, but not really. Now we're directly defining them. That is in your notes somewhere, but I just wanted to recognize that. That's the difference between X bar and mu. X bar being from a statistic, from a sample, and mu being from a population identified as a parameter. Okay, so I definitely wanted to look at this to kind of show what a sampling distribution is. So here's what should happen. Okay, we're talking about this chips, these blue and red chips in the example. They are 50-50. We know that because they were put into a tub or into a bowl or whatever you want to call it. It is 50-50. So the true population parameter is 0.5. Okay. So there's 100 blue and 100 red. So, but if you take one SRS, you can see it's 40-60, right? 60% blue, 40% red. Well, then what happens if you take another one? Well, this one is 55% red, 45% blue. Well, then what happens if you take another one and then another one and another one and another one and you keep repeating that process? This is the sampling distribution, okay? Approximate sampling distribution of repeating these samples over and over again. It's what I had you do when I had you roll the die 10 times and then record that. So I had each of you do that 10 times and then 24 students. So there's 240 basic samples in our sampling distribution, if you will, for what we did with our rolling of the die. So here's your sampling distribution. Notice the center is right around what it should be. Okay. It should be around 0.5 because that's what it's supposed to be. But notice we can get things that vary off of that. Notice we got one that's here and a straggler that's here, and that can happen. Okay. So that's just one thing to be aware of. Okay. So there is something that I wanted to show in terms of sampling distributions, a little activity here. I need to share another screen with you. So this is a way to simulate, instead of us doing things over and over and over again, rolling die or tossing coins or anything like that. Here's the parent population. It's approximately normal. Okay. And we're going to simulate taking samples, and then we're going to find the mean of those samples. So this is finding the sample data, and then this is finding that mean. So let's just say we took a sample of 5. Okay, so you're taking, that's a small sample. Okay, so we're going to take a sample of 5, 1, 2, 3, 4, 5, and then boom, the mean is right there. Okay, so this is, you took a sample of 5 and they gave you these results. Okay, and then this is the mean of those 5. Okay, so let's do that again. So then I will take another sample of 5, and then there's their average. Okay, and then we'll take another sample of 5, and then there's the average. And then you take another sample of 5. Okay, so if you keep repeating this process, and then you find the mean of those 5, this is a sample. So this is one sample, and then you're finding the mean of that. Okay. And if you repeat that process over and over and over again, so let's repeat it. So I did it. Let's repeat it. I'm doing it 5 times. Instead of doing it, when I do animated, it does it 1 time. This means I'm doing 5 samples of 5. Okay. So 5 samples of 5, 5 samples of 5, 5 samples of 5. Notice I'm building a distribution. What happens instead of, I want to do it faster. It's a simulator. It's a computer that can simulate things. Let's do 10,000. And let's do another 10,000. And let's do another 10,000 of sample size 5. So we're still sampling 5 people, but we're doing that 10,000 times. Okay, well, how about if I do it 100,000 times? So I'm going to ask 5 people something, and I'm going to ask that. I'm going to do 5 samples 10,000 times, and then I'm going to do it 100,000 times. What happens if I keep doing that? It looks normal. Okay, it looks approximately normal. What happens when you do sampling and you find the mean? Notice you get rid of these stragglers. There's hardly any outliers, right? The variability is cut down. Okay, when you do a sampling distribution, when you think about finding the mean of each sample, you are cutting down on your variability. Okay, so when you take the whole entire population, anything can happen when you ask individual people. But when you average those 5 individual people, it's very unlikely that you're going to get this. You ask one person, you can get this. Yes, 5 people and average that, it's unlikely to get this, because out of averaging 5 people, it goes towards where the center actually is. Okay, and that leads into we just mentioned variability. That leads into our bias. or our unbiased. Okay, you can see this is unbiased because the center is basically in the same spot. That's unbiased. If the center was shifted off, we call that bias. We talk about biased data. If you collect biased data, it's worthless. You don't want to use it. So that's why we try, when we collect actual data, we want our sample to be unbiased. That means that the centers are the same. Okay. So you can change the sample size of these. So if I clear these, you can change the sample size. And now if you animate, you're taking a size 10 sample. Okay, so change the sample size, you animate, you can see that there were 10 people that were 10 things that were sampled. And then if you do that again, you're going to take another sample. Notice there's one down here, but where does the mean go? Oh, the mean of this is here. Okay, so this is one sample. Anything can happen in one sample, but if you repeat this process many, many, many times, here, let's go many, many, many times. Here we go. Oh, many times it gets to be normal. Okay. So that leads me into, well, what if we have a skewed population? Okay, what if we have a skewed population and we're going to take random samples of size? Let's just stay with size 10. 10 is not a very big size. It looks fairly skewed. And there's the mean of that data set. Well, and then we do it again. Boom, boom, boom. We'll let it, we're taking a sample. It looks kind of skewed, right? What happens if we do it 10,000 times? What happens if we do it 100,000 times? Kind of looks normal, doesn't it? It is. When your sample size gets large enough, this is the binomial approximation that we talked about. When your sample size is large enough, and how large is large enough? Well, with a proportion with binomial, as long as you meet NP greater than or equal to 10, n times 1 minus p is greater than or equal to 10, then you will be approximately normal. Okay, is this exactly normal? No, it's approximately normal. In terms of something with a mean and standard deviation, as long as your sample size is 30 or larger, that's large enough. Okay, so those are like the two checks that you could say approximately normal. So this is just showing that even if it is skewed, if you're taking a sampling distribution, it will be approximately normal if your sample size is large enough. Okay, if I clear it again and if I just do it 5 times, that's 5 samples of size 10. That's not approximately normal. If I do it again, nope. Nope, not really. But if, as I keep clicking, or if I just go straight and make it 10,000, make it a lot, it's getting more approximately normal. Okay, that's kind of what this is trying to show here. This is a sampling distribution of repeating it and then finding the average of each of those samples. Okay, I did not have you find the average of your samples, but this is just taking the next step in sampling distributions. Okay, so the last couple things I just want to talk about real quick with sampling distributions, and then we'll be done. So sharing, I don't know if that's shared right or not. Okay, so population size is not so important. It's really the sample size that matters. Okay, if you're taking a sample size of, let's just say 10,000 people, it doesn't matter whether the population is 10 million or 1 million, you're still taking the sample size of 10,000. If you are taking a percentage of your population, then the population size does matter because you're taking different sample sizes, right? 5% of a million is not the same number as 5% of 10 million. So the 10 million sample, the 10 million population size will give me a higher sample size, and that will be less variable and will be better because the percent of a higher number is a bigger number. Okay, 5% of a bigger number is a bigger number. So if you're doing it from as a percentage standpoint, well, then a population size does matter. But if you're just looking at the sample size is a standard sample size, then the population does not matter in terms of how big it is. Okay, and that's kind of what this is saying here. The other thing I just want to talk about is variability, bias, and shape. We've already talked about the shape. talked about the variability a little bit, talked about the bias a little bit, but I think a visual is helpful. Okay. And students that have taken physics, they use different terminology. It would be nice if we could use the same thing, but we talk about precise and accurate. Okay. Those are the same type of things that we're talking about with bias and variability. It really means the same thing. We're just giving it a different name. So if you already understand precision and accuracy, it's the same concept. So you can see letter A here is high bias. We're not hitting the center. Okay. You want to hit the center or be close to the center. That's bias. So that's low bias. I want to have a low bias. I want to be close to the center. So this is high bias, but it's low variability. If you were shooting arrows or a gun at this, your gun is very, I think the word is accurate. It's pretty accurate. It's getting into a very big cluster, or maybe I have those words backwards, accurate and precise. I always forget those two. But this is, they're hitting, it's hitting the same place over and over and over again. We need to make some corrections to get it hitting it over and over and over again here. So in this is low bias because you are around the center. The center is, it's a good thing you're around the center, okay? But there's a lot of spread. The variability, you don't want to be shooting all over the place, okay? But you are around the center, if you will, okay? And then on the next slide, we have the other two. So this one is high bias, high variability. This is just bad, okay? You're not clustered together and you're not near the center. So you got high variability, high bias. This is the worst case scenario. You don't want that. This is what you want. You want to be really clustered together and then right around the center. This is what you want. So you want no bias or low bias. It's hard to get rid of bias altogether. You want low bias, low variability. That kind of shows our example here of what we would like with our sampling distributions. Okay. Let me know if you have any questions.